Good afternoon, everyone. Today I'm here to explain about my research topic, which is geared quasi-CVT for electricity generated wind turbines. First of all, I would like to thank Dr. Salim Massoud to suggest this problem, and the mentor of this project, Dr. Guy Bernard, for his great contribution. In this research, we are only considering about horizontal axis wind turbine. That means the axis is horizontal of this wind turbine. So normally, when we are going to the Oklahoma, especially in Wickramarachchi, you can see these kind of wind turbines. The process of this wind turbine is make wind power to make wind power to electricity. First of all, I would like to explain what is CVT means. CVT means continuously variable transmission. For continuous variable transmission, they give output constant speed for any input speed. That means if we use different speed as an input, that gives the same output. And the second thing is they usually use belts because the reason is they can give large amount of force. So normally that's why they are using belts. When we talk about wind turbine is located 200 to 300 feet above the ground level, and each blades large enough 60 to 130 in length. And normally what the wind turbine is doing, you can see the blades over here. When wind enters to the blades, it's going to be rotated. So after that, the rotation is connected to the lower speed shaft, then it's connected to the gearbox. Finally, it's going to the generator and make the electricity. What is a gearbox? A gearbox is a device to convert one speed to another. So this is a sample of a gear system, and in this case we are only speaking about spur gear. Spur gear means the axis is parallel to other gears. So in here, this axis is parallel to this one. So that's why we call spur gear. This is a simple outlook of the wind turbine. First, you will see the wind blades, and this is the low speed shaft. Then gearbox. This is a simple gearbox, 2 gear, and generator and control electronics. When we look at deep look about the wind turbine, you will see the blades, like I told before, and rotor, pitch system, brake, low speed shaft, gearbox, generator, and the controller. The controller means it's decide which gear system we need for wind speed. Like if it is 5 RPM, this will decide which gear system, which gear ratio we have to use. The objective of this project is to design a gearbox which has 1000 RPM, less than plus or minus 16. That means 984 RPM to 1016, while allowing the wind turbine speed vary between 5 RPM to 30. So this is again a simple picture about the wind turbine. So you can see the blades and main bearing, gearbox, then disc, brake, and the generator. This housing called nacelle. To design a gearbox, we have to follow very basic three things. First of all, we have to determine number of stages. How many stages we have to use. If we increase the stages, it will give more combinations. That means there are more possibility to get an accurate result. And the same thing, determine the number of satellite gears. Normally it's like this. Gearbox has a sun gear, and the sun gear is connected with satellite gears. So depending on the satellite gears, we can get more combination. And we have to decide what is the size of each gear. That means the radius. For our case, we use this is our gear transmission. We have 5 stages, 1, 2, 3, 4, 5. So here is the wind turbine blades, and this is our first main gear, sun gear. The gear with the bar showing the driving gear, and the gear over here is the driven gear. So the gear on here is showing idle gear. That means this is just giving help to transmit the rotational motion to these gears. So I would like to say these gears are not connected. Like these axes are not like, if it is 5 RPM over here, this can be 7. So these gears are independent from each other. So here is the satellite gears, and this is the generator, which is making electricity. This is the front view of a gear. Think this is a sun gear, and for our case, we use 5 satellite gears, 1, 2, 3, 4, 5. So our minimum gear is 6.614, and the maximum gear is 18. While I was doing the calculation, we need to know like what is the angle to get to have, like, for example, we use 5 satellite gears, and this is the sun gear. So if we are using 5 satellite gears, we have to think about, like, according to the radius, they might be overlap each other. If it is overlap, the gear system is not going to work. So it should not overlap. So to not overlap, what is the minimum angle? So I decide this has a same radius for all circles, and normal trigonometry, 360 divided by 5, 72 degrees. This is the minimum requirement to have gears for satellites. And not for overlapping. While I was doing this thing, I assume this one is R, lowercase r, and this one is capital R. So in back slides, we already got to know this angle should be 72. According to trig, this is going to be 54. So after doing the calculation, to not overlap with these two gears, this is the requirement. Simple R is less than 1.1526 capital R. This means simple R means the radius of this circle, and the capital R means the radius of these two circles. So then we have to find the gear ratio. Gear ratio is the product of driven gears over product of driving gears. But in this case, to be easy, we use 1 over gear ratio. That means the product of driving gear over product of driven gear. So this is what we end up with. This is our formula. RT I would like to explain. RT is this one, the main sun gear, and this radius is 100 centimeters, and the last one is RW. You will see later. This is 50 centimeters, and the gap between this one to this one is I use as a symbol epsilon, which is 10. So RT is 100 centimeters, RW is 50, and this is the epsilon. So we found out many results. First of all, we found 1128 gear combinations, and to do this research, we use wind speed 5 to 30. We increase the speed, like for example 5.0, 5.2, 5.4, like that, and then after that we get the gear ratio as a function of gear combination, and final graph we got like quasi CVT graph. So this is the gear ratio as a function of gear combination. In here, this is the combination, gear ratios. We got 1128 combinations, and our gear ratio is starting with 200. For this, we start with the small gear, which is 6.614. So, and we end up with the large gear, 80 centimeters. So this is how the graph looks like. If we start with the large gear, and if we end up with the small gear, this is the graph looks like. For our gear system, these are the gear ratios gears we use as a radius. First gear we use 6. For first sun gear we have 2 satellite gears. So each satellite gear has 6.614 and 18. And the second sun gear we have 5 satellite gears. So it's like 6.614, 9.44, 45, 14.6, 26.4 and 77. And third gear, these are the results. Fourth gear, these are the results. And fifth gear, these are the results. And after using this radius, we got a nice graph. Normally, for this problem, we can go with 984 to 1016 RPM for the generator. But after using those results, we get an efficient output, which is it's only vary 998 to 1002. This is like quasi CVT. So this is what I end up with my research. And I would like to thank again Dr. Salim Massouz and Dr. Guy Bernard and Dr. Megale to have this great opportunity. If you have any questions, don't be hesitant.